What's up, gamers? Welcome to another CS014 SI video. My name is Cody, and I'll be teaching you about Dijkstra's and Bellman algorithm. In the beginning of Dijkstra's algorithm, we initialize all vertices distances to infinity and the predecessors to 0 or null. While the unvisited queue is not empty, we're going to start popping off from the top. So from the starting vertex, we're going to start comparing the current vertex's distance and edge to another adjacent vertex. If the total amount of distance is smaller than the adjacent vertex's distance, we replace it. We check all adjacent vertices, and once we are done, we repeat for the next vertex from the queue. Additionally, Dijkstra's algorithm cannot work with negative edges since it may result into incorrect shortest distances. For Bellman-Ford's algorithm, it is the same as in going through the graph, applying the small distances between vertices. The only difference is that it can work with negative edges. Sometimes in these graphs, one iteration will not guarantee the shortest path due to negative edges. So in order to combat this, we will go through the entire graph n vertices minus 1 times. Additionally, at the end of the graph, when it's finished, we check if any distance is negative. If it is, then the shortest path does not exist. So let's take a look at this example. We start out with a graph like this. We set all vertices distances to infinity and the predecessor pointers to null or 0. We pop the 0 out of the queue and start checking the adjacent vertexes. In no particular order, we check vertex 1. The starting vertex is 0, and the edge between vertex 0 and 1 is 4. We add those two numbers up, and it's 4, which is less than infinity. So the vertex 1 distance is 4, and the predecessor for the vertex is 0. And then moving on to another adjacent vertex, vertex 2, the distance of the current vertex and the edge is equal to 5, which is less than infinity also. So vertex 2 has a distance of 5 and a predecessor of vertex 0. Now checking with vertex 4. The distance from 0 to 4 is 1, which is still less than infinity. So the vertex 4 has a distance of 1 and predecessor vertex 0. Since there are no more adjacent vertices for vertex 0, we move on to the next value from the queue. For vertex 1, we check the vertex for 2. The distance of vertex 1 is 4, and we add it with the weight of 2, which is equal to 6, which is not less than 5. So then we move on to the next adjacent vertex. For vertex 3, the distance is going to be 1's vertex, which is 4, plus the edge from vertex 1 to 3, which is also 4. It equals 8, which is less than infinity. So we then set vertex 3's distance to 8 and the predecessor to vertex 1. Then we pop the queue, and which is now onto vertex 2. For vertex 2, the only vertex that is adjacent is vertex 3. The current vertex distance is 5, plus the edge, which is equal to 1, which is basically equal to 6, which is also less than 8. So we replace vertex 3's distance to 6 and its predecessor to vertex 2. Vertex 2 has no more adjacent vertexes, so we then move on to the next value off the queue. For vertex 3, the only vertex that is adjacent to it is vertex 2. The distance is 6, and the weight of the edge is 5, which is equal to 11, which is not less than 5. So we then move on to the next on top of the queue. For vertex 4, the only vertice that is adjacent to it is vertex 2. We take the distance of 4, which is equal to 1, and the edge, which is weight of 7, which equals to 8. But that is not less than 5, so we don't do anything. And since there are no more adjacent vertices and the queue is empty, we are now done. Now for Bellman-Ford's algorithm. We do the same thing as Dijkstra's algorithm, but now we go through the graph n vertices minus 1 times, all starting from the starting vertex. Starting with vertex 0, we check vertex 1, which is distance of 0 plus 2, which is less than infinity, so vertex 1 has a distance of 2 and a predecessor of 0. For vertex 2, it's going to have a distance of 0 plus 3, which is also less than infinity, so vertex 3 is going to have a distance of 3 and a predecessor of 0. Moving on to the next vertex of the queue, vertex 1 has an adjacent vertex of 3. We take the distance, which is 2 plus 1, which is equal to 3, which is also less than infinity. So vertex 3 has a distance of 3 and a predecessor of 1. We now move on to vertex 2. It has a distance of 3 minus 3, which is equal to 0, which then is also less than 2. So the distance is going to be 0, and the predecessor for vertex 1 is vertex 2. Now moving to vertex 3. It has no adjacent vertexes, so we are done for this iteration. Usually in Dijkstra's algorithm we would stop, but due to this negative weight from vertex 2 to 1, there's going to be a couple things. The correct path is going to be wrong, since we're going to go from vertex 0 to 2 to 1 to 3. The total weight of that trap path would be 1, but vertex 3 has a distance of 3. And that is when we assume that if we are traveling from vertex 0 to vertex 3. And this is why Bellman-Ford's algorithm goes n vertices minus 1 times. Eventually, we're going to have a graph like this, where after the second iteration, vertex 3 would have the correct distance of 1. And for the other iterations, no other changes would be made. And that's pretty much it. Well, I hope you guys enjoyed this video. If you have any further questions, please leave a comment below. And I hope you have a good rest of the day.